So for this video, I'm gonna really try to build an intuition for understanding uniform circular motion. We will first discuss about what uniform circular motion actually is, and then we'll work our way to derive the equation for calculating the centripetal acceleration, which is actually v squared over r. So basically, our story starts with, well, uniform acceleration. Uniform. Now, this is a really powerful two words that has a lot of conceptual meaning to it, and I'm going to try to break it down thoroughly for you. Uniform circular motion. So basically, when we're talking about circular, well, it just means in a circular path, duh. Circular path. Motion means something that moves, so movement. So this is actually a part of a kinematics lecture. So uniform means constant. Alright? Now, it actually really depends what we're thinking to be constant. In this scenario, our speed is constant. Our velocity is not constant. Not velocity. Alright. So uniform acceleration is all about trying to accelerate towards the center. So you might have heard about centripetal acceleration. So I'm just gonna try to build a more intuitive sense about thinking about it. So let's start with a circle, because circular motion. So our circle kind of looks like this. Gonna work our way upwards. Yeah. So here's our circle, and let's say I've got a bowl in here. Kind of looks like this. And it is in circular motion around this track. So maybe it's you taking your dog for a walk. Maybe it's you running 10 kilometers lap. But yeah, this is a point particle, which is going through uniform speed. Okay, constant speed, not velocity. So our velocity vector at this point should kind of point, well, here. Nope, that's not really what I want. Delete. I'm just gonna draw it through a hand. So, alright, so the velocity vector is kind of like this. So that's our v. If it were here, the velocity vector would probably point to something like this. Another v. If it were here, it would be somewhere here. That's our velocity vector. Now, the change in the velocity direction as we're seeing in this cases counts as acceleration. So basically, the magnitude stays constant, but since our direction is changing, we are witnessing acceleration. So we know that acceleration is a vector, so we must put the vector sign above it, is equal to the change in the velocity per unit time. So that's delta t, change in time, and the numerator is actually the change in velocity, which we can write as vf minus vi. And we can consider this to be vf, and let's say this to be vi. Alright, just for the sake of it. Now, if you wanna really solve this thing, we must go for the vector subtraction, since this is present. So if we kind of really move a little bit onto the side and try to draw it, let me just change the color. Magenta seems good. Alright, so this vector, we're subtracting the final. We're subtracting the initial from the final. So the initial, this thing will get subtracted from here. So VF will stay as it is, kind of looks like this. So VF. Remember that the size of the errors will stay the same because that's the magnitude. What we are talking about is the direction, the change in the direction. So that's what's changing. And the VI kind of looks like something like this. It's like coming here, like this. That should be like VI. But since we're not adding, we're subtracting, what we are going to do is draw it with the opposite arrows. So it will go like here and here, hence that's VI. So to not make things complex, I'm just trying to erase it and pick up my pen again. So alright, so if we subtract this, the vector sum will just be this part, the direction here. So that's our acceleration. Now the cool thing is, this is actually called, oh, this is too thick of a pen. Okay, this is called centripetal. Let me just make it cooler. Okay, centripetal acceleration, which you can see that we were here right at the center, somewhere here. This is the center. So, and this is our this is our radius r, and basically this acceleration is toward the center. So if you can kind of think about this in this way, it's basically the same drawing is basically to be here, right? So the acceleration would be right above here. Sorry, wait. Acceleration would be right here towards the center. So that's how, using vector sum, we can conclude the fact that it will be pointing right toward the center. Now, if we want to talk about, now we'll be talking about the equation for the centripetal acceleration, which seems pretty important. So I'm just going to give it to you for the sake of it right now, and then we're going to try to derive it from our understanding of the universe. So the equation that gives us the centripetal acceleration, just a little subscript C, is actually v squared over r. That's it. And if we want to look at the towards deriving it, it will involve drawing a circle. It's the very same circle, something like this. And it would be nice if I could have my planes. Right over here. Change the color. I guess you can't really see the thing. Okay, just make this white as well. Okay, that's perfect. We can think about this as the center, this point to be the center. So basically we're thinking about the fact that maybe we have got a point particle right over here. Okay, that's a big chunk of particle, but yeah, works. And then we have its velocity vector. the point something like this. That's really fat, but I hope you get the point. It just points up like this. That's our velocity vector. And this velocity vector could actually be broken down into components, into its x and y components. So if we are breaking it down into components, this will be the Vy, and this will be the Vx. Alright, perfect. Let me just label these axes, because why not? So let's say this is positive x, and this is positive y. What we can also see is a triangle right over here. I hope that's making sense to you. You can think about it. This angle to be theta. This is a right angle, so that's nice, perfect. This is a right angle as well. So if this is theta, this is also theta. And hence this is also theta, because that's what our 5th grade geometry tells us. Alright, now what we can think about is that they look very similar. So we can use the concept of similarity in triangles, right? Similarity. So, similarity, yeah. So what we can say is that the vector Vi is the same as V as X is to R. This is R and this is our X, because they are similar. So if we write that in vector notation, it will look something like this. Vy over V is equal to X over R. And then we can also do that for the other way. So that will be simply, well, if you can work it out, you can imagine it. It will be Vx over V is equal to Y over R. So that's some solid things if you think about it. Now we can really, what we really want to think about is this part, this V and this V. Okay, so we're gonna make this these subjects and this the subject as well. So this is basically the j hat direction, and this is basically the I hat direction, because that's I and this is y, so j. So we can write this as V, the vector V is equal to V times X over R g theta plus V y over R I theta. Now if your teacher looks at this, he or she will throw in a big objection that you have to first write y and then write j. That's exactly what I'm going to do now. So Vy over R I theta plus V times X over R j theta. Alright, pretty neat. Now what we can do is, if we take the derivative of V, basically dv over dt gives us, well, the acceleration, and that's exactly what we're looking for. So we're going to take the acceleration for both the components, and it should look something like this. So let's just do it in a different color, say purple. Okay, acceleration will be equal to the Vr, take the derivative of, we're taking this and this because these are constant, the y is changing, so the derivative of y is just multiply it, and then we go just basically Vy. in the I hat direction plus v over r again, because these are constant, and take the derivative of x. So that's basically vx to j hat. That is basically in vector terms, but we want to really think about it in terms of magnitude. So we'll just put an absolute symbol in front of it, basically 2 bars, and then we can take the square roots of whatever's inside to get the value. So v over r times v whole squared plus v over r times, sorry, I just messed up y, so vx whole squared. That should give you, if you multiply it together, that should be, well, v squared over r squared times v, and then this will cancel out. So initially, like at the end, what we're going to be left with is, and you take the square root out, and there's a square, so the square on r will be gone. So basically what we will be getting is v squared over r, and you can like say that it's the same thing that I showed you before. So that's basically it. Oh, and another thing I'd like to mention is that from here we see that the velocity and the acceleration cannot be in the same direction, because this and this actually depend on each other, because I hat, this is y, and x hat, this is j hat, and this is x. So they do not depend on each other, so they depend on each other, and hence the acceleration and velocity are not in the same direction. Thank you so much for your attention.